Today we're going to study about factorization of polynomials, specifically polynomials of x over rational numbers. However, let f of x be any polynomial in this set, but this can be written as a ratio of some polynomial over some integer, where g of x is a polynomial over integers and c is an integer. For example, if we have a polynomial of like this over rational numbers, 1 over 4x and 1 over 2, this can be written as 1 over 12 times 8x squared plus 3x plus 6. So if we set this part as g of x, then 12 is an integer and g of x is a polynomial over integers. So all the coefficients are integers. So if we want to consider factorization of these polynomials over rational coefficients, we can only it's sufficient to consider polynomials over integers. So our goal here is to show that if a polynomial, let's say f of x in z of x, so integer coefficient polynomials, non-trivially factors in q of x, so it can be factorized as a polynomial over rational coefficients, then f of x factors non-trivially in z of x. So if we take the contrapositive of this statement, if a polynomial of integer coefficients does not factor in this set, then it does not factors non-trivially in this set of polynomials with rational coefficients. Now let's define a few notions. Let f of x be a polynomial with integer coefficients. Let's write this as a 0 plus a1x plus and so on, an times x to the power of n, where all these coefficients are integers. Then the greatest common divisor of these coefficients is called the content of this polynomial. And if this greatest common divisor is 1, so if GCD of a0, a1, and so on is equal to 1, then we say f of x is primitive. And so, as we have seen before, suppose f of x is a polynomial with rational coefficients, then we can write this as g of x over c, where g of x is a polynomial of integer coefficients and c is an integer. And if we factor the greatest common divisor of the coefficients of g, then we can write this as something like this. And the content of this is content of this is 1. So this is a primitive polynomial. So this D is the greatest common divisor of coefficients of g of x. Let's see an example. Suppose f of x is 14 over 5x squared, 28 over 3 x, and 21 over 2. So let's factorize this. 5, 3, 2, 84, 280, and 315. So if we find the greatest common divisor of these three integers, that would be 7. So this 5 times 3 times 2 is 30. So this would be 12 and 40 and 45. So 7 is the greatest common divisor of these three integers. So this polynomial has the content of 1. So therefore it is a primitive polynomial. Now let's prove a little lemma. Let f of x and g of x be polynomials with integer coefficient, be primitive. And then suppose there are integers c1 and c2 such that c1 times f of x is equal to c2 times g of x. Then we have c1 is plus or minus c2, and therefore f of x is equal to plus or minus g of x. Okay, let's prove this. So first of all, let f of x be a0 plus a1x plus and so on, and an times x to the power of n. And since this is supposed to be a primitive polynomial, then the greatest common divisor of these coefficients, a0, a1, and so on, an is equal to 1. So therefore, there exists some integers. Let's see. C is used, so let's use t1, t2, t0, t1, t2, and so on. Integers such that t0a0 plus t1a1 plus and so on, tn an is equal to 1. Actually, we have proved a similar theorem for two integers, but the similar result holds for any number of integers. So if their greatest common divisor is 1 or d, then there exists some integer satisfying this equation. And now, by assumption, since c1 f of x is equal to c2 g of x, this implies c2, this one, divides so c1 times a1, and sorry, c2 divides c1. Maybe I should write c2 divides c1 a0, c1 a1, c1 a2, and so on, c1 an. So in particular, therefore C2 divides T0 okay, C1 A0 plus T1 C1 A1 and so on Tn C1 An. But this, if we factor this C1 out, then we have C1 0 T1 A1 Tn An. But this one is equal to 1. So C2 divides C1 times 1. So it divides C1. And we can do apply the similar logic opposite. Right? So from this we can say that if we define g of x in terms of some explicit polynomial like this, then C1 divides C2 times all the coefficients of g of x. Then similarly C1 divides C2. Therefore we have thus we have C1 is equal to plus minus C2. And if we substitute this into this, then we have f of x is equal to plus or minus g of x. And we are done. The next lemma is called Gauss's lemma. Gauss's lemma. And that says let f of x and g of x be polynomials with integer coefficients, and they are primitive polynomials, and then the product f of x times g of x is also primitive. We prove this lemma by contradiction. So suppose f of x is a0 plus a1x plus and so on up to let's say am x to the power of m, and g of x be b0, b1x, and so on, and bn x to the power of n. And also, let's write f of x times g of x as c0, c1x, and so on. And the highest degree is cm plus n to the times x to the power of m plus n. And we are assuming am is not 0 and bn is not 0, and therefore cm plus n is not 0. Okay, now suppose a prime, let's say p, divides all of these coefficients. Okay, and now since f of x and g of x are primitive, P does not divide all of A i's and b j's. Right? So some of these coefficients, a0 to am and b0 to bn, they cannot be divided by this prime p by assumption. Okay, so let's assume that p divides a0, a1, and so on, up to, let's say, a r minus 1, but not a ar. So that means ar is the first coefficient p cannot divide. Okay, and also p divides b0, b1, and so on up to bs minus 1, but not bs. So that means bs is the first coefficient p can divide. So p cannot divide. Okay? And ar is the first coefficient p cannot divide. Okay? Then consider the coefficient c r plus s. Okay, so if we calculate this product and compare the coefficients, then c r plus s is the following sum: a0 times br plus s, and a1 and br plus s minus 1, and so on, and ar minus 1 times bs plus 1. Then we have ar times bs, and plus ar plus 1, bs plus 1, and so on. After all, we have ar plus s and times b0. Okay, now by the way we chose p and r and s, p divides a0. Oh, sorry. P divides a0, a1, ar minus 1, and so on. And also p divides b0 and b1 and up to, oh, wait a minute, this should be bs minus 1. So p divides bs minus 1. So that means all these terms here and all these terms, each of these is divisible by p. And we're assuming p is the common divisor of all these coefficients. So p divides c r plus s. So therefore, p should also divide ar times bs. So by the property of prime numbers, this implies, which implies p divides ar or p divides bs, which is a contradiction. Because by assumption, p cannot divide ar or bs. Therefore, this is a contradiction. So after all, f of x times g of x is primitive. And we are done. Let's see one example. Consider the polynomials 2x squared plus 3x plus 1. This is primitive. And also x squared plus 2. So these are primitive polynomials. And let's take the product of these two polynomials. And if you expand this, we have 2x to the power 4 and 3x cubed and 5x squared plus 6x plus 2. And as we can see, so this is 2, 3, 5, 6, 2, and the greatest common divisor of all these integers is 1. So therefore this is primitive. Next, we use Gauss's lemma to prove the following lemma. Let f of x be a polynomial with integer coefficient, with its degree being n, which is positive. And then, if f of x does not factorize in z of x, so this cannot be expressed as a product of two polynomials with integer coefficient into the product of two polynomials of degrees r and s, where r and s are between 0 and n, and r plus s is equal to n. Then f of x does not factorize in q of x into the product of two polynomials of degrees r and s. We prove this lemma by contradiction. So suppose f does not factorize in z of x, but factorizes in q of x. So we can write f of x is as a product of two polynomials, say g of x and h of x, where g of x and h of x are polynomials with rational coefficients. Okay, and of course f of x is a polynomial with integer coefficient. Okay. Then we can, as we have seen before, this can be written as c0 and f0 of x, and c0 is an integer, and f0 is primitive, and g of x, say c1 over d1 and g0 of x, and h of x can be written as c2 over d2 times h0. And so f0, g0, h0, they are all primitives. And C0, C1, D1, C2, D2, they are all integers. So we can write in this way. So if we substitute these into this expression, we have C0 F0 of x and C1 D1 G0 of x, C2 D2 H0 of x. So multiplying both sides by D1 and D2, we have C0 D1 D2 F0 of x, C1 C2 G0 of x, H0 of x. Now remember, f of f0, g0, h0, they are primitives. And by Gauss's lemma, this product, so by Gauss's lemma, this product, g0 of x times f0 of x is primitive. So we have primitive on the left hand side, another primitive on the right hand side. And from a previous lemma, we have so this integer is equal to plus or minus of this integer. So C0 D1 D2 is plus minus C1 C2. And also f0 of x is equal to plus or minus the primitive of the right hand side. So if we multiply both sides of this by C0, this is this, but the left hand side is f of x. However, this is, so by assumption, we didn't make it explicit, but we are assuming that degree of g of x is equal to the degree of g0 of x, which is assumed to be r, and the degree of h of x is equal to the degree of h0 of x, which is assumed to be s. And also the coefficients of g0 and h0, they are all integers. So g0 of x is and h0 of x, they belong to the polynomials with integer coefficients. So this is a contradiction. So this shouldn't happen because of the assumption. So we are assuming that f of x does not factorize in z of x, but in the end we have this factorization where f of x is factorized into the product of two polynomials with integer coefficient. So this is a contradiction. Therefore, contradiction. And we are done. Now we can prove our main result. This is a theorem called Eisenstein's criterion. This gives a sufficient condition to decide whether a polynomial can be factorized or not. Okay, so let f be a polynomial with integer coefficient. Let's say f of x is a0 plus a1x plus and so on, an x to the power of n, and an is non-zero. So the degree of this polynomial is n, and assume the following. Okay, so suppose there is a prime number such that that satisfies the following three conditions. So P divides A0, A1, A2 up to AN minus 1, and 2, P does not divide AN, and 3, P squared does not divide A0. Then f of x is irreducible as a polynomial in Q of x. So as a polynomial with rational coefficient. By the way, in the case of the polynomial ring, irreducible means this polynomial cannot be factorized into the product of two other, non-trivially factorized into the product of other polynomials. Let's prove this. We prove by contradiction. So suppose f of x is not irreducible. So this implies that this f of x can be factorized into the product of two polynomials in Q of x in this ring. But this in turn implies that f of x can be factorized in z of x. So let's write f of x as the product of g of x times h of x, where g of x and h of x are polynomials with integer coefficients. Okay, and more specifically, let's write g of x as, let's see, b0, b1x, and so on, and br x to the power of r, and h of x as c0, c1, and cs, and x to the power of s, and cs is non-zero. And these degrees are between 0 and n. Okay, so by assumption, this is possible. This decomposition is possible. Now consider the coefficient a0, which is b0 times c0. Now, by assumption, p divides a0, therefore p divides b0 times c0. But since p is a prime, then this implies p divides b0 or p divides c0. However, by assumption 3, p squared does not divide a0. Therefore, p does not p divides only one of b0 or c0. Not so it does divide not both b0 and c0. So it divides only one of these. Okay, so for the sake of argument, let's assume, so suppose, without losing generality, suppose p divides B0 and P does not divide C0. Okay, uh, so the opposite is okay. I mean, we can equally assume P does not divide B0 and P divides C0, but it's just a symmetric argument, so we can just assume this one. So anyway, and if P divides all of B0, B1 up to BR, then P divides, so this implies P divides all of A0, A1 up to AN, because each of these coefficients A0, A1 and so on, they contain at least one of these beads. So this means these coefficients of F are divisible by P. However, this is a false statement, because by assumption P does not divide AN. So this is a false statement. So what this means is that there exists an integer, a natural number, such that k is greater than 0 and less than or equal to r, and P divides B0, P divides B1, and P divides up to bk minus 1, but P does not divide bk. Okay, there is such a k. So now we consider ak, which can be expressed as let's see, bk. Maybe we should write b0 from here. B0 ck plus b1 ck minus 1 and so on, and b k minus 1 times ck c1 plus bk times c0. Now, from this assumption, P divides this up to this term, and also by assumption P divides AK by this assumption. We're assuming okay, so actually there shouldn't be equal sign here. So therefore P should divide, so the left hand side is divisible by P and the right hand side is divisible by P except for this one. So this one should be also divisible by P. So BKC0. But by this assumption, this is a contradiction. So since P is a prime, this implies P divides BK or P divides C0. But neither of these is true, because the way we chose BK, this is not possible. And by our assumption, C0 is not divisible by P. So this is a contradiction. So therefore, f of x is irreducible in Q of x. And we are done. So what's nice about this theorem is that Eisenstein's criterion is that we can decide whether a polynomial can be factorized or not without ever actually factorizing. So let's see a few examples. Uh, First example, let p be a prime number. Then the polynomial x to the power of n minus p is irreducible. So this is a polynomial with rational coefficients. This is irreducible. To be more explicit, the coefficient of the zeroth order term is p. So it's divisible by p, but it's not divisible by p squared, right? And the coefficient of x to the power of n is 1, and since p is a prime, it does not divide 1. And other coefficients are 0, so they are all divisible by p. 0 is divisible by any numbers, in fact. So according to Eisenstein's criterion, this is not this cannot be factorized, so it's irreducible. And the next example, consider this polynomial: 21 plus 6x squared plus 9x cubed plus 4x to the power of 4. Of course, this is a polynomial with rational coefficients, and this is not this is irreducible. If we consider the prime number 3, okay, 3 divides 21, 6, 9, but it does not divide 4. So, and p squared is 9. 9 does not divide 21, so the Eisenstein criterion is satisfied. Therefore, this polynomial is irreducible. Finally, let us prove that the polynomial f of x equal to 1 plus x squared plus and so on up to x to the power of p minus 1, where p is prime, is irreducible. To see this, so we can calculate this summation as regarding this as a geometric sequence, sum of geometric sequence, we can prove that this is equal to x to the power of p minus 1 and divided by x minus 1. Now let us change variables by setting x, let's see, let's put y equal to x minus 1. So we have y plus 1 to the power of p minus 1 divided by 1, y. And by using the binomial theorem, this is equal to, so the numerator is equal to 1 plus p choose 1 times y plus p choose 2, y squared and so on, and p choose p, and y to the power of p, and minus 1, this one, all divided by y. Okay, and since this 1 cancels this y, and every other term contains y, so this y can be cancelled. And what we have in the end is p choose 1 plus p choose 2, y, and so on, and p choose p, y to the power of p minus 1. Now, P divides this, and every coefficient except for this one. Okay, so this is equal to 1, so this is not divisible by P. But every other coefficients, they are uh, divisible by P. And also, P choose 1 is equal to P. So it's not divisible by P squared. Therefore, this is irreducible. And that's all.